Okay, good morning, everybody, and thanks for inviting me to this workshop. This is really a beautiful venue, and I'm happy to present here. So, yeah, I'm going to talk about image reconstruction methods for energy resolved CT. So how do I get the slides back? Oh, there we go. Okay, so I'm Emil Sidky from the University of Chicago, Department of Radiology. So I'm coming from the medical imaging side of things, and where's the pointer? Is this it? Oh yeah, Tally's my experimental collaborator on this work in spectral CT. She's from Marquette University. We have a local in-house theoretician from the stats department at U of C, Rena Barber, who I ask all the hard questions to, and then Xiaochuan Pan's my boss. So, all right, how do I advance? Okay, but the arrows aren't working. Oh, there we go. It's up and down. I see. All right. Okay, so here's the outline of my talk. I'm going to give an introduction to spectral CT, and then I'm going to talk about the different image reconstruction methods that are being used or being developed for doing image reconstruction in spectral CT. So Simon already, in his really nice overview talk, he already gave a summary of these three methods. So we have two-step methods where you do the spectral processing after image reconstruction, or you could do the processing in the data space and then do reconstruction. And my research lately has been focused on doing this one-step approach where you take the transmission data for the CT and directly try to recover the spectral CT images. And I'm going to show some results. We'll see how far we get. I mean, please ask questions if you don't understand anything. So, I mean, this part of the talk here is, I can make it shorter or longer, you know. All right, so we're going to start very basic. So how many CT people are familiar with the CT model? All right, web, yeah, very good. Okay, so it's about half the people. So you don't mind if I go on with this part of it. But okay, as far as the data modeling is going for a CT, it's very simple. All we're doing is we're shining X-rays at the object and detecting the transmitted intensity. So, and it's just a straight line path. So you have an X-ray source here emitting X-rays at intensity I0, and you detect them at intensity I. So in the standard CT modeling, you ignore the spectral aspect of the radiation. And so all you have is an exponential extinction of this intensity I0 to get to the transmitted intensity I. So in standard CT, this is just processed by doing the negative log of I over I0 to isolate this path integral here over the object. And so if you measure over multiple rays through this object, you should be able to recover the attenuation map from the line integrations of the various rays that you've measured. Okay, so that's a continuous model, but for most of this talk, I'm going to be using iterative methods. And in iterative image reconstruction, we don't actually directly solve the continuous to continuous X-ray transform model. So what we do is we discretize the image by pixelizing it usually, but there's other representations that Simon alluded to. And so what you do is you just form a really large matrix system with G being the data, X being the discrete representation of the X-ray transform, and F is your pixelized representation of the image. So basically the matrix elements of X are just depicted right here. So you can use the line intersection method where you, in order to calculate the contribution of the pixel F of K, all you do to the ray measurement G of L is you just calculate this line intersection of the ray through the pixel. Okay, that's pretty clear, right? Everybody's following? Good. So this is an extremely sparse matrix, all right? Because most of the rays will miss this pixel. Just wanted to point that out, all right? So now this talk is going to be about spectral CT. So what do we do? What are we doing here? So in reality, the spectra for CT across X-rays is quite broad. We do not have monochromatic spectra. And we can exploit this by shining, or to get some spectral information of the object to help us determine like more physical properties of the object. And on the measurement side, what we need to do is we need to expose or have measurements with different spectral sensitivities. So there's multiple ways to do this. So probably the most common way is just to vary the voltage on the X-ray source. So you can imagine like doing one scan at one energy or doing another one at another energy, or you can switch quickly from view to view or over or less quickly over like different arcs of the scan to get different spectral radiation that you'll detect. You can do source filtering also. You can have also dual layer detectors where on the detection side you have different sensitivities. And then lately, which has also been my interest, is using photon counting detection, where you actually have the detector detect the transmitted X-rays one photon at a time, and there's some energy information that's also being recorded with those detected photons. From a mathematical standpoint, you can do as many windows as you like. So this would just be, or energy windows as you like. And so that is just referred to as multi-window spectral CT. But in application, by far the most common thing is to just have two energy windows. And so application-wise, there's a bit of a distinction between dual energy and multispectral CT. All right, so coming back to this iterative picture, so all we do is, or the model picture is, we're just adding another index to the source brightness and the transmitted intensity. This index is W, which is labeling the energy window. And sometimes for the transmitted intensity, I'll use C when I'm talking about counts of photons, all right? So that's like alluding to the photon counting detection. So the transmitted model now is a little bit more complicated. So here I'm going back to the continuous setting. So we have those same exponentials with the line integrals, but now the attenuation that you see is a function of energy and space. Right? So there's a weighting over the spectral response and integration over E, and so now your transmitted data depends on your ray and the energy window sensitivity. All right? Okay, so I've written down this model again here. So how do we deal with this? So mathematically, this is a much worse problem than the original image reconstruction problem, right? Because you have a spatial dependence to the attenuation map, and you have an energy dependence, right? So now you've gone from 2 to 3 dimensions if you were doing 2-dimensional scanning before, or 3 to 4, okay? But there's a huge simplification that you can do. So we know that the subjects that we're scanning are composed of a finite number of materials. So you can do a materials expansion. Okay. So the materials expansion will then allow you to separate the energy dependence from the spatial dependence. So each material will attenuate X-rays with a known dependence. So you can actually look up the tables for these attenuation curves for different materials at the NIST website. So here's attenuation curve for water, calcium, and the contrast agent iodine. All right. So then instead of having the continuous energy index, now we have a more discrete materials index. So it's a little bit more complicated though, because the mechanism for attenuations are actually not as numerous as a number of materials, okay? So in this diagnostic X-ray range, actually, there are two main physical processes going on. There's a photoelectric absorption, which has a dependence of about 1 over energy cubed. That's why you see all these curves kind of doing this kind of thing. And then there's Compton scattering, which is approximately constant in energy. Then you also have some atomic processes like this K-shell electron ejection, which gives rise to these kinds of lines. That's why, so like you see the absorption's coming down, then all of a sudden it's jumping up again. That's because you're able to knock off K-shell electrons. So what this does for imaging is that you have a huge jump in contrast at this energy. And so that's why you use a material like a K-edge material like iodine for dual energy contrast. If your sensitivities are going on either side of this edge, you will see this contrast light up, right? Everybody still with me? All right, okay, good. So mathematically, though, the fact that you only have few processes creates a little bit of an issue when you do the materials decomposition, because you have many more materials than there are physical processes. So you can't just write your body as a sum of a bunch of all the materials that are in there, because you won't, the actual rank of this mu table, as I call it, where you just put all the materials as rows of a matrix, is much lower than the number of materials, right? So you won't be able to recover the coefficient of all those materials. Is that point clear? Okay. So let's start to move on to image reconstruction. So we're back here at this energy resolved model. And we have the materials decomposition. So now I'm going to discretize it. And this is actually my discrete model for spectral CT. So I have the exponential here, and F is my materials maps, and X is X-ray projection, and mu are those discretized mu curves that I was showing on the previous slide. And we have a spectral sensitivity. I haven't put all the summations in there just to make it clear. But the sum over I does the energy summation, and K does the projection, and the sum over M is a materials expansion. And just here's the list of all the indices. W is energy, L is transmission rate, I is energy index, materials, and pixel. All right? So, so what are we trying to do in spectral CT? So we're trying to get this turn these transmitted photon counts into the material maps, or we're trying to recover, we're trying to recover these material maps F from these transmitted photon counts, okay? And once we have those, then we take those from those, so those maps, those material maps F are what we're solving, but those are not necessarily the images that we'll present. I mean, sometimes they are. So if we're interested in contrast agent imaging, for example, we would want to show the distribution of iodine contrast, all right? But sometimes we want to do other things. You can combine those material maps and form an estimated monochromatic image, or you can make an image of a mass density or electron density, which is of use in radiation therapy. Okay. So yeah, mathematically, the thing that makes this difficult is that if you put this model into an optimization framework where you're minimizing some kind of data discrepancy term, this will become a non-convex optimization. All right, so I'm going to run through the methods now. So this, by far, is the most common thing is done clinically, is this two-step method with the post-reconstruction processing. So this is probably like, if you're going to approach this problem, this is probably the very first thing you would try. because you already know that CT works, right? With that old model, we know we're getting decent images, right? So what's the closest thing to what we were doing before that we can do now? You can just take this model here, just take the transmitted counts, divide it by the incident counts at that energy window, take the negative log, all right, like we were doing before, and this approximately is going to give you the projection of the material maps multiplied by some kind of spectral weighting, all right? And so you can get this approximation just by doing a Taylor expansion on the exponential and the log, all right? And then you can just use your favorite reconstruction algorithm to get these Fs, and then combine the weighted images as you like. So here's just an example from a clinical scanner. This is reported in this radiology article here, where a patient was scanned at two different energies, 80, where one of the X-ray sources scans was at 80 kVp and the other at 140. So this is the 80 kVp image, and this is a 140 kVp image. I think this is a contrast scan, right, Webb? Yeah, that's what I thought. So this has contrast agent in it. I don't know, it's a little bit difficult to see the noise characteristics, but when you blend the images, you can see that you have the contrast of the low energy scan, but less noise than you have up here. So this image is more noisy than this one. So you can just do this blending, all right? So to improve your image, but you can also do some quantitation. So that's, when you're doing contrast agent imaging, sometimes people want to know like exactly how much contrast agent is in a region. So you can do a kind of a histogram analysis, all right, of this kind of image where you just take the pixels of the low energy image and put on the x-axis the pixels of the high energy image on the y-axis, and just look at the scatter plot, and then you can actually separate materials this way. And for example, here this just shows a histogram for iodine and bone, which would normally be difficult to separate on just a regular CT, but in this dual energy setting, they kind of separate. And then now you can go back to the image, and the pixels that you identified as being bone, you know they're bone, you can mark them that way, and the iodine ones you can mark as iodine, and you can do a little bit of quantitation there. All right, so any questions about this, the post-processing method? All right. The nice thing about this post-processing methods, you don't have to worry too much about the calibration of the system. You don't really have to know the spectral responses exactly. You can just do things like that scatter plot, or you can just combine the images until they look nice, all right? As we go down the list here, though, things get a little bit more complicated. So now I'm going to talk about the pre-reconstruction processing. Okay, so the idea of the pre-reconstruction processing is quite simple. So this one is we're not going to make any approximation now. So we come back to this counts model where we have the counts in terms of the materials maps. And so now we're going to break this model up into two pieces. So what we're going to do is just write the counts as a function of the sinograms, the material sinograms, or the sinograms is just essentially the collection of line integrations through the materials maps, all right? So we're going to go from counts to line integrations, and then once we have the line integrations, then we're going to do our favorite reconstruction algorithm, all right? And so for this one, I'm just going to run through kind of a seminal paper in the spectral CT literature, just to show like how this is working. And actually this work took advantage of this new photon counting detection. And so actually in this paper here, that's not 2018, it's supposed to be 2008, sorry about that. They had a spectral sensitivity which was divided up to 8 windows, all right? So for this one, you do actually have to calibrate the detector. You have to know these spectral sensitivities, okay? And so they went to a monochromatic X-ray source and went and took their detector there and measured the spectral responses of each of the windows that they're detecting with their detector, right? And for their materials expansion, they actually had a 4-term expansion. So they divided up they expanded this attenuation map into the 2 physical processes, the photoelectric and the Compton scattering, which are dealing with non-K-edge materials, and then added in 2 K-edge contrast agents, gadolinium and iodine. Okay? So in order to then do the sinogram decomposition, or to go from the counts to the sinograms, then they just estimated G from the counts with the transmission Poisson likelihood model. And so this is a test phantom that they used in that paper. So it has water, and PMMA is kind of like a tissue-like plastic in terms of X-ray at least. And then they had different vials of gadolinium and iodine, and they wanted to see if they could resolve those. And so here we go with some images. So they did that decomposition of the counts into the various sinograms, and then reconstructed those 4 basis functions, and then combined those into different images. And so here what we see are the monochromatic images going from 25 keV windows up to the 80 keV windows. All right. So any questions then about the post-reconstruction or pre-reconstruction?
Can you come back to the slide, the one before this?
Yeah.
I don't understand why. Sorry, just the curiosity, because maybe I missed something. Why is like the peak higher for lower energies than?
Yes. So like you see these peaks, and then you see these long energy tails.
Yes.
Yes, those are non-idealities in the detector. So in principle, with an ideal photon counting detector, the way it works is when a photon comes into a detector pixel, it should be able to detect whether that photon is above a certain threshold and below another threshold. But there's a whole bunch of physical processes going inside the detector which kind of messes that up. And so one of them is that the charge from one pixel can get split in amongst a couple of pixels. So it doesn't only hit the one, all right? So that's called charge sharing. And so then it's actually detected, it goes down into a lower energy window. And so that's why you see these long tails.
Like this seems like you have more counts for lower energies, or I'm misunderstanding this.
Oh no, these oh wait a sec, I can't actually see the axis there. Oh, normalized count rate. Yes, so
Okay, sorry. It's not okay. Nothing.
yeah.
Okay.
Okay, is all clear? All right, very good. All right, so now I'm gonna, so the 2-step stuff is not as easy as the the pre-reconstruction method's not as easy as the post-reconstruction method, so it's not used nearly as commonly as the previous one. So the 1-step stuff, that's purely in the research domain now. So this is where we're trying to go straight from the counts to the material maps. And so there's a lot of work on that, but but I'll just go run quickly through what we're doing in this area. So the advantage of doing the one-step methods, probably the main advantage is that you do not need to have registered projections. So in the previous method where I showed the processing, where you're doing the processing before the reconstruction, you need to have, for each ray, you need to have registered measurements for all the windows, okay? Because you're going to combine those measurements to get the sinograms and then go from the sinograms to the reconstructed images. But for the one-step method, we can take any kind of configuration of rays and energy windows, all right, and combine that all in the data fidelity term, and then out will pop the reconstructed materials maps. And then there's also some opportunity to do direct regularization in the image domain. That's also kind of nice, but probably this is the main advantage, okay? And so this is an example of one of the optimization problems that we're using in this setting, where we minimize a transmission Poisson likelihood of our counts model with the counts that we have. And then we've thrown in these coefficients alpha, which allow us to scale the spectral sensitivity of the windows. All right, so those are unknown scaling factors. And the reason we're doing that is because it's actually kind of hard to do the calibration properly. So we want to have the ability for us to have the data inform us about the spectral sensitivity. And so that's what the alphas are doing. And then we're going to also do regularization in the image domain. So we're going to constrain the total variation of each of the materials maps. So we like to work here in this constrained format instead of penalizing the total variation, because these gammas have a little more physical meaning. All right, this is not like with a penalized thing where you're a little bit further removed from what what the meaning is of the penalized coefficients. And particularly for spectral CT, we like this because if we want to adjust the total variation for only one materials map, and not have them all change, you can only do it this way, all right? Because if I change a penalty, then of one of these coefficients in the penalized formulation, then all the total variations will change. But in this constrained form, I can change one of these coefficients and only that materials map will change, all right? So this is the optimization problem that we're interested in, and it's a non-convex optimization because of the complexity of the model. And we are developing a derivative of the Shambo-Pock-Primal dual algorithm that can handle this non-convex thing called MoCA. Right? And in order to determine all these constraint parameters, we use validation. And so here's just an example of us using this method on a two materials decomposition. So this is a chicken wing, and we've decomposed it into an aluminum map and a PMMA map. And here's a combination of those two materials into a monoenergetic map, okay? So this is if we only use a total variation constraint. And I don't know if you guys can see it, but there's some rings in there, right? And so those rings come from the fact that we're not doing a perfect job with calibration, okay? So if you have a miscalibration of a detector element, it'll show up as a ring in the image, all right? If we throw in those scaling factors that, the ability to, those unknowns which allow for, the data to adjust the scaling of those spectral responses, you see we can get rid of those rings, right? But, you got to be a little bit careful there, because if you don't constrain that part of it, it's a non-identifiable problem, and you can get weird artifacts. So there is a constraint factor that you do have to take care of, all right? So how much? 10 minutes. 10 minutes? Okay, so then I'll go on and talk a little bit more then, because so what I've shown here is a two materials decomposition. All right, the reason why I'm using aluminum and PMMA here is because aluminum is a little bit bone-like and PMMA is more soft tissue-like. But the real use or interest in spectral CT, at least on the medical side, is imaging contrast agents. All right, so if you're going to do contrast agents, you need more materials. So that means you at least have to go to 3 or 4 materials decompositions. And actually, things get a little bit more complicated. Oh yeah, so here's some summary of algorithm. I'll just skip over this stuff. Okay, yes. So one of the issues that we had when we went to more materials is that just the convergence of the algorithm itself was slower. Okay, so here I just show like a very short summary of a simulation that we did, which involved a 3 materials decomposition where we have a rods phantom involving aluminum decomposition and PMMA and a vial with gadolinium in it. All right. With the old algorithm that I showed you the 2 materials results for, the convergence of the algorithm was much too slow. So here in this side of the, or in this figure, I'm just basically showing the gadolinium image as a function of iteration number. And so going from 100 to 2000 with just that straight algorithm, it takes a long time for that gadolinium image to settle down into something recognizable as a gadolinium map, all right? And so that's where we had to develop this preconditioner, which we applied to the Shambo-Pak algorithm, this block diagonal preconditioner, and this allowed us to improve the convergence speed substantially so that already at the 100th iteration, we see something that's somewhat representing the gadolinium image, okay? So that was a kind of a nice development, because then it allowed us to do some real experimental studies with 3 materials. And so let me just show you a result of an experiment that involved metal imaging. So metal is also an issue in CT because metal is highly attenuating and from the spectral, and so if you just have metal in your CT subject, it'll create lots of streaks. So here I have that same phantom, but now we have the possibility to put steel rods in there. So here's just with standard processing, if I have a non-metal object, you have a very clean image, but if I put metal rods in there, you see these nasty streaks. There are ways to compensate for metal, but yet if you still do that, you still have lots of streaks in the image. But so now with this multi-material decomposition of the object, we can clean this up even more. So now we do the expansion into the 2 soft tissues, or the soft tissue and the bone, and we can also include metal. So just the raw reconstruction with the spectral CT method has substantially reduced streaks. And we can do even better by using the fact that we do not need to have all the information for all the energy bins. I mean, all the detector pixels. So we know that when we have rays going through the metal, that the data that's going into the low energy sensitivity windows is very suspect, because basically it's all the photons that are going through metal are going to be more or less high energy photons. And so we can just throw away that low energy window and still perform the reconstruction. And if you do that, you see clean up the image substantially, right? So then after this metal project, we wanted to come back to contrast agent imaging. So this is my last thing. So here then we had a little issue with system calibration. So the problem, before with a 2 materials method, we still had some issue with system calibration, but it wasn't as bad. If we just used the same methodology and went to 3 materials, then yeah, the decomposition into the three materials was not representing very well the underlying reality. So we ended up having to improve our system calibration. And so this is what we do for system calibration. The reason why I want to show it to you is because it is an inverse problem. It's by itself. So here's our transmission measurement that I showed you on the early slides. All right, we need to know S, right? So what we do is we expand S as a product of a model of the X-ray source and the detector model. Okay, so this was the new part that we are adding in this segment of the talk, is that we've taken a model for the sensitivity of the detector. And we have a model, there are published models for X-ray sources, so we're using that. And then there's another issue, is that there's something called pulse pileup in photon counting detection. So as you can imagine, the difficult part of photon detection is that the count rate is pretty high, right? And as the count rate gets higher, then the photons start to pile up on top of each other and get measured as one. And so then the intensity as a function of, or your measured intensity as a function of true intensity is not a straight line, but it's just kind of rounding off like this, all right? And so what we have is a quadratic model that will hopefully correct the measured intensities to give us the ideal intensity thing. So then on top of, so we have this quadratic thing, we have a spectrum model and a detector model, and then we also have a low parameter polynomial fit. So how do we determine all these parameters in this model? Is what we do is we take transmission measurements through known materials, all right, at different thicknesses. And so from that, from those measurements, we get these parameters of this model. And so if we do that, then we ended up getting much better quantification in this 3 materials thing. But this is still you know, an open problem here, is like how best to deal with the spectral calibration. All right. So this is the last thing I want to show. So I'm just going to summarize all the different methods. So I showed you basically 3 different reconstruction methods for spectral CT. So the clinical one, the 2-step post-processing method. Then there's a 2-step pre-reconstruction processing, and the 1-step spectral CT reconstruction. So the advantages here is that the calibration is straightforward. You know, you can just do everything in the image domain. And you can use standard reconstruction. You do need 2 scans, but they do not necessarily need to be registered because you're reconstructing them independently. So the problem with this thing is that you're sensitive to beam hardening artifacts, because those streaks that I showed you in the metal thing, because you are not really using the accurate spectral response model, right? But this, you know, this depends on the spectral window width. If you somehow manage to get very narrow spectral responses, this is not a big deal, right? For the 2-step pre-reconstruction processing, the calibration is more challenging. You can still use standard reconstruction algorithms, but you need registered spectral data. But this at least does deal with the beam hardening artifacts, and you can do quantification. Okay. The 1-step spectral CT reconstruction, the calibration is still challenging. I've put this advanced reconstruction algorithm with a red box because for application it's a disadvantage, but for us, you know, as theoreticians, mathematicians, this is the fun part, right? So we like to develop this, so it's an advantage for us. And then you don't need registered spectral data, so you can do flexible scan configurations, and you have accurate handling of the model, so you have beam hardening, artifact correction, and quantification. Right, thank you for your attention.